So in last class, we looked at the rotational transformation, and the most important transformation that you should remember is the rotation about z-axis. We are going to use the right-hand coordinate system, and in the right-hand coordinate system, curl your right hand, thumb is x, first finger is y, z is coming out. So this is your x, this is your y, and the z is coming out. When you curl your fingers in the direction of rotation, if your thumb is pointing towards the positive x or y or z, that rotation is positive, which means if you look at this rotation, that is positive. If you look at this rotation, that is positive. If you look at this rotation, that is positive. For almost all the forward kinematics problems, we are just going to use the rotation about z, and that is the only rotation that you should remember. This approach is radically different from approaches given in any of the robotics textbook. So please understand this concept very, very carefully. So what you have is you have this x, y, and z, and I'm gonna rotate this coordinate frame. So this is x. I'm gonna call this x0. I'm gonna call this y0, and we are gonna rotate about z0. So z0 and zx, z1, z1, and z0. And this frame after rotation is something like this. This rotation is called theta z because this rotation is about theta. And please note, this rotation theta z is positive. Say theta z is positive. So in last class, I derived this rotation transformation, but I'm gonna do it again. So check this out. We always look at the projection of the new frame. The new frame is x1, y1, z1 onto the old frame, which is x1, y1, x0, y0, and z0. And then to find out the projection, please understand the projection of x1. This is x1, this is y1. So projection of x1 onto x0, it's a unit vector, which means magnitude is 1. So 1 multiplied by cosine theta z. So this will become cosine theta z. And note that when we resolve the vector, this is the direction the vector is resolved, which means its components are in this direction. Now notice projection of x1 onto x0 in the same direction as x0. Projection of x1 onto x0 is in the same direction as x0. So this is going to be positive cosine theta z. Are you with me? Now projection of x1 onto y0 is going to be sine theta z. But please note that projection of x1 onto y0 is in the same direction as y0. So that means this is going to be positive sine theta z. X1 has no relationship whatsoever with z0. So this becomes 0. Now let's start with y1. Now y1 is the resultant, which means it is the hypotenuse of the right angle triangle. So the projection vectors will be in the directions I have shown. Can you see that the projection vectors are going up and left? That is resulting into the total y1. So if I were to write down the projections again, this projection is going to be cosine theta z, and this projection is going to be sine theta z. But now I want you to understand, it's very important, projection of y1 onto y0 is cosine theta z in the same direction as y0. So which means I'm going to get projection of y1 onto y0 is going to be cosine theta z. Projection of y1 onto x0 is in the leftward direction, which is opposite to the positive x0. So it's going to be negative sine theta z. So minus sine theta z. Clearly, y1 has no relationship whatsoever with z0. z1 has no relationship with x0. z1 has no projection on y0. z1 and z0 are aligned. So 1. This is called as the rotation matrix. This rotation matrix is written as R01. And the reason this is written as R01 because we are going from 0th frame. This is the old frame. Old frame. This is the new frame. This 0R1 is called an orthonormal matrix. Why orthonormal? Because the rows and columns are perpendicular to each other and they span a space which is actually right angle triangle. So this is an orthonormal. Which means the inverse is equal to transpose. This is extremely important. In last class, we started with an important concept about the coordinate frames. Coordinate frames are extremely important when you solve a robot kinematics or robot dynamics problem. And in today's class, what I'm going to do is, I know all of you are super intelligent. So I'm going to make you aware of the things that you already know. The material that I'm going to discuss is something that you studied in high school. Trust me. But what I'm going to do is I'm going to make you aware of that lost knowledge so that you can connect the dots. So please try to understand. In the last class, we talked about few rules. And these rules, whether you use DH parameters or whether you use rotation matrices, these rules are consistent. So rule number one is Z axis must pass through joint. There are two types of joints. One is a revolute joint. So if you have a revolute joint or a hinge joint, the direction of rotation is this, which means your Z axis should go up or down, but it needs to be along the axis. You can also have a prismatic joint, and prismatic joint is shown something like this. And then this is the direction the joint extends. So for the prismatic joint, this should be the Z axis. It doesn't matter whether it is going towards right or left, but it needs to go through the axis. So Z must go through the joint. Rule number 2, XN must intersect Zn minus 1. Xn will intersect Zn because it's a right angle triangle system. But Xn, which means X1, must intersect Z0. X2 must intersect Z1. X3 must intersect Z2. Everyone understood this? And the last rule is the right hand coordinate system. Now I'm going to rework the previous the problem that we started. In the previous problem, what we had is we had an R parallel to R robot. So if you remember, I had a robot which was drawn something like this. And this is the simplest type of robot that you can actually solve. This is not a new robot. basically, if you look at this robot from top, this robot is nothing but a pendulum with basically you have two masses. So if I were to draw the robot, you would notice in the current configuration that I have shown, this is like the first pendulum. This is the hinge. And then there is this second pendulum, and this is another hinge. So you have two hinges which are connected to each other. Now what I'm going to do is, this is the robot. This is the first revolute joint. This is the second revolute joint. And this is the end effector. First revolute joint is parallel to the second revolute joint. So this configuration is R parallel to R. It's a 2 degrees of freedom robot. So you have theta 1 and you have theta 2. You have theta 1 and theta 2. And I'm going to give you some dimensions. This dimension, it does not change. It's fixed. So this dimension is A1. This dimension is A2. This dimension is A2. I'm going to call this dimension as A3. And I'm going to call this dimension as A4. So which means if you were to look from top, the two pendulum model, you would see this as A2 and A4. In the top view, the vertical dimensions A1 and A3 will not be visible. If you take a side view, only then this would be visible. Everyone understood this configuration of robot? In case if you are wondering how does this robot look like, I can show you a pictorial view. You can have a motor. On top of the motor, you can have a link. At the end of the link, you can have another motor. And at the end of the motor, you have another link. So this is how this robot is going to look like in current practice. So you have this first robot hinge. You have the second robot hinge. And at the end, you have an end effector. This is called as the configuration diagram. Configuration diagram must be drawn when the robot angles are 0, which means theta 1 is 0 and theta 2 is 0. Now, what I'm going to do is I'm going to use these rules and set up my axes. First, how many joints do I have? I have 2 revolute joints. By the rule, z-axis must pass through the joint. So without any comment, I can say this is going to be my axis z1 or z0. I'm going to say this is going to be my axis z1. And this is going to be my axis z2. Please note, there is no joint at end effector. There is no joint at end effector, but I have assigned a coordinate system which is aligned with the previous coordinate system, and that is because of a purpose. So my z0, z1 and z2 are the axes that I have defined. Now I need to start with x0. There is no x zn minus 1. So there is no z minus 1. So I can assign my x. I can say this could be my x. I can say this could be my x. My x could go in this direction or my x could go in any direction. So right now there is no constraint. Your x axis can be anywhere. But for the sake of simplicity, I would use this as my x axis. So this is going to be my x0. Now, since I have x0, I have z0, I align my x, I align my z, so I get this as my y. So this is my y0. Do you agree with me? Now what I need to do is I have to go to the second frame, which is frame 1. I have z1. I need to find out x1. I have two choices. My x1 could be like in this direction, or my x1 could be in this direction. Now please try to understand, these are axes. They can be extended infinitely. So if I were to look at there are two options. If I look at this option as x1, we discussed this in last class. Can you see that x1 is intersecting z1 because it's a triad, and x1 is intersecting z0. So rule number 2 is satisfied. Do you agree with me? However, for a minute, assume that instead of this axis, you use this as your x-axis. Now you would notice that this x1 is intersecting z1, but it is not intersecting z0. And if you are wondering why not, then actually you can take a look at that figure from the side, and you would notice, and I'm going to show it to you here. This, if I were to choose this configuration, please note, this is going to be my x, and this is going to be my, this is going to be my, let me use a different color. This is going to be like, so there will be, this will be like z here, and this actually does not intersect with my z1. So this is not the right configuration. I should not be using this as x1. This should be my x1. Everyone understood this? This is extremely important. Now I have z1, I have x1, y1, and z1. So curl your fingers, and now you have this as y1. Same thing for this end effector. I have z2. I would assume this to be x2, and this becomes my y2. So now the coordinate system is set up. Everyone understood the coordinate system? This is the first and most important step. Now we are going to derive the rotation matrices. Now here is the thing. For rotation matrices, rotation matrix is the product of two matrices, the rotation matrix and the projection matrix. So I'm going to write this something like this. Check this out. 0R1 is the product of two matrices. First one is the rotation matrix that we derive. So this matrix, you shouldn't forget, which is cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. This matrix is never going to change. This matrix would remain as is, no matter what type of problem you are solving. This guy is called as the projection matrix. And why is this projection matrix important? Projection matrix is needed because we are dealing with two frames. The first frame is the 0th frame, and the second frame is the first number 1 frame. So we need to make sure that these two frames are aligned, because if they are not aligned, the axes won't be in the same direction. So the general process for this is, what you do is same thing, x1, y1, z1, x0, y0, z0. This is the exact same transformation we have used before. Now check this out. My x1, can you see that this x1 is aligned with this x0? X1 is aligned with x0. So same direction, 1. X1 has no relationship with y0. 0. X1 has no relationship with Z0, 0. Now let's look at Y1 and Y0. Can you see Y1 and Y0 are aligned? So this is 0, 1, 0. Can you see Z1? So Z1 is right here and it is aligned with Z0. So which is 0, 0, 1. In this particular case, the projection matrix is an identity matrix, which means even if I multiply by this 0 R1, my result is not going to change. And this is going to be cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. So when I multiply the rotation matrix by the projection matrix, I get this final resultant matrix. Everyone understood this? Now, what we need to do is we need to formulate something called as the homogeneous transformation. Now, this rotation transformation gives me the rotational relationship between the old frame and the new frame. I also want to know the translational relationship between the old frame and new frame. How far these two frames are. Because please understand, frame 0 and frame 1, they are not on top of each other. They are further apart. So I want to come up with a relationship that gives me the distances between the old frame and new frame. And in last class, I kind of touched upon this. This information is captured in the homogeneous transformation. So homogeneous transformation is the transformation from the old frame, this is the old frame, to the new frame, wherein the first 3 by 3 matrix is the rotation matrix. The first 3 by 3 matrix is the rotation matrix. Cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. So this is the first 3 by 3 matrix. Now the last column, the last row will have 3 zeros and last row, last column would be 1. Now the question is, what goes here? So what goes here? What goes here? What goes here? Now once again, I will write down. Here, the distance between 0th frame and first frame around X in 0th frame. So what I want is, I want the distances between the old frame, which is this frame, and this frame, but they should be in the previous coordinate system. What does that mean? Now I want you to note that my 0th frame is here. My first frame is over here. And I want to find out what is the distance between the 0th frame and the first frame about x naught. Looking at the top view, you can say that this distance is nothing but A2. But this relationship is valid when theta 1 is 0. If theta 1 is non-zero, which means imagine if your theta 1 is non-zero, if it is something like this relationship is going to be A2 cosine theta 1. Do you agree with me? Which means what I should write down here, it's extremely important. Now I'll spend 1 more minute on this. This is the key. Whenever you have a homogeneous, once you get your homogeneous transformations right, forward and inverse kinematics is piece of cake. So you got your rotation matrix, and here you need to find out the displacement relationship between the new frame and the old frame with respect to old frame. Everyone understood this? New frame, old frame, but with respect to old frame, which means I need to find out how far uh, zeroth frame, how far the first frame is away from the zeroth frame around x naught, around y naught, and around z naught. And those relationships should be valid no matter whatever is the joint angle. So the relationship here should be valid whether my theta is 0, theta 1 is 0, theta 1 is 90, theta 1 is 180, theta 1 is 370, whatever it is. Everyone understood this? But at this point, I need the distance between the new frame and the old frame in the coordinate frame of the old frame. And that is going to be A2 cosine theta 1. Are you with me? This frame is going to be A2. This is y distance. This is going to be A2 sine theta 1. And the z distance, A1 is fixed. A1 is not changing. So I can just write this down over here, A1. Are you with me? Now, our homogeneous transformation for first frame and the zeroth frame is done. This is now what we are going to do is we are going to go from the first frame to the second frame. So 1 R2. So we are going from the first frame to the second frame. This rotation matrix, please don't talk. Please don't talk. This rotation matrix will comprise of the baseline rotation matrix multiplied by the projection matrix. No matter what problem you solve, as long as you are dealing with a revolute joint, the first rotation matrix is not going to change. This is going to be cosine theta 2. Yeah, here theta 2, cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2. Do you agree with me? Then you will have 0, 0, 0, 0, 1. Now, what is my new frame? My new frame is x2, y2, z2. What is my old frame? My old frame is my old frame. And this is my new frame. My old frame is x1, y1, z1. Now we will do the same thing. Now I want you to look at this diagram. Can you see that x2 is in the same direction as x1? Yes. Y2 is in the same direction as y1. Yes. And z2 is in the same direction as z1. Yes. Which means if I were to populate the projection matrix, it will be x2 is aligned with x1 in the same direction. If the direction would have flipped, then I would have added a minus sign. But both the directions are same. X1 is pointing and x2 is pointing in the same direction. So 1, 0, 0. Y2 is pointing in the same direction as Y1. 0, 1, 0. Z2 is pointing in the same direction as Z1. 0, 0, 1. Do you agree with me? Yes. Which means this again is an identity matrix. This is not by accident. Why do I have projection matrix as identity? Because I deliberately try to keep my frame number 1 and frame number 2 as aligned as possible with frame number 0. If I would have, it is absolutely possible to flip the axis in other direction. So for example, it is not wrong. Instead of x1 going in the positive direction, I could have used x1 going in the negative direction. Still, it would have been okay. But my projection matrix would have a negative sign. Everyone understood this? Yes. My last frame, which is the frame sitting on top of end effector, is same aligned as the previous frame x1. That's why I get a very nice identity matrix. Now I need to populate my homogeneous transformation. Once again, in homogeneous transformation, I'm relating first to second. So it will be 1H2. Do you agree with me? Yes. And I'm going to copy the rotation transformation. Please note, this is an identity matrix, so no need to multiply. This matrix is going to remain the same. So I would just copy this matrix down. Cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. And I need to populate the last row. It will always be 0, 0, 0, and there will be 1. And now, same thing. And I'm going to write this again. We are relating frame 1 and 2. 1 is our base frame. Frame 2 is our second frame. So now I need here the distances between frame 2 and frame 1. Here there should be x distance, here there should be y distance, and here there should be z distance. Everyone understood? Yes. Distance between the new and the old frame in the coordinate frame of the old frame. What does it mean? It means go back here. Check this out. Now, if you look at from the top view, can you see that this distance again is A4? And so the x distance between the frame 1 and frame 2 is A4. You agree with me? When theta 2 is 0. When theta 2 is non-zero, correct, you are going to have, and again, I need to be very clear. This is going to be my theta 2. This is going to be my theta 1. It's extremely important why I have drawn like this. Imagine the thetas are defined from their zeroth position. So the first joint rotation is with respect to its zero position. Second joint is with respect to its zeroth position, which is nothing but the reference frame of the original link. Please understand, this angle is theta 2. Everyone understood this? So if I were to write this down here, this is going to look like A2, no, A4, cosine theta 2, A4 sine theta 2, and then I would be left with A3. Are you with me so far? Once again, the homogeneous transformation contains the information about the relative rotation of the coordinate plane and the relative displacements between the coordinate plane. Displacements are vector, so the directions are extremely important. Now, this relationship is only between frame 2 and frame 1. But notice, A4 cosine theta 2 is around or in the same direction as x1. A4 sine theta 2 is in the same direction as y1. And A3 is in the same direction as z1. Everyone understood this? Now what I want to do is, I want to solve forward kinematics problem. Forward kinematics problem. Forward kinematics problem. Yeah. X and Y axis in the top view. X and Y axis in the top view. So this is going to be my Y0. This is going to be my X0. This is going to be my y1. This is going to be my x1. Actually, I want to draw a nicer and bigger picture. Just bear with me, and I will draw. But let me define this problem. Because trust me, in next 10 minutes, you will have moment of enlightenment.
You said distance between two frames in the zeroth frame.
In the previous frame,
In the
previous, it could be zero, it could be first, depending upon where you are. So forward kinematics problem. Forward kinematics problem is given joint angles, which is theta 1 and theta 2. Find position of end effector in x direction, position of end effector in y direction, position of end effector in z position. What? Uh-oh. And this is all expressed in x0, y0, and z0 frame. x0, y0, and z0 frame. So distance of end effector will be with respect to the 0th frame in x0, y0, and z0. Everyone understood this? Okay, now, since we are doing forward kinematics, let's do inverse kinematics. So 2 chapters in one shot. So forward kinematics problem is given theta 1 and theta 2, which are nothing but the joint angles. Find the end effector position. So you program the joint angles and the robot goes to a specific position. Inverse kinematics problem. Kinematics problem is given end effector x position, end effector y position, end effector z position. Find theta 1 and theta 2. Are you with me so far? Now here is the major problem. Look at the pendulum problem that we are trying to solve. So we have 2 pendulums, and if I give you an end effector position, say this is my first coordinate frame, and if I give you this end effector position, if this is my end effector position, this can be reached by these 2 angles, which means I can have maybe theta 1, and then I can have like theta 2, or the same end effector position. Please note, the same end effector position can be reached by something like this, which means I could have theta 1 and I could have theta 2. Are you with me? What does it mean? It means forward kinematics problem has a unique solution. Inverse kinematics problem can have one solution, can have multiple solutions, or may not have any solution. Do you agree with me? Example, if my if my end effector position is somewhere over here, no matter what I do, my robot is not gonna reach that position. Everyone understood this? So forward kinematics is going from joint values to the end effector position. Inverse kinematics is working from the end effector position and finding out joint angle. Everyone understood this? Now, when I believe you me, I studied robotics. I did this 4 or 5 times in my as a student, as an undergrad, grad, then during my PhD, all that stuff. and I have to go through very, very nasty mathematical formulae, simplification, and trig identities to solve inverse kinematics problem. So basically do trig substitution, do some manipulation, add square terms, subtract square terms. But we don't do that generally nowadays. What we do is we set up the forward kinematics problem, find out 0h1, 1h2, 2h3, 3h4, how many h's are there? And we solve the forward kinematics problem as 0h2. Why 0h2? Because number 2 is my end effector frame. 0 is my reference frame. So this is nothing but 0h1 multiplied by 1h2, and I use MATLAB to multiply 4x4 matrices. When I was a student, I had to do all these calculations by hand, and it was a pain. So when we solve forward kinematics problem, what we are going to do is we are going to set up the problem and just find the homogeneous transformations. And then we will use MATLAB to solve the forward kinematics. So what would forward kinematics give me? Forward kinematics will give me the relation for Px, which is the position of end effector in x coordinate as a function of theta 1 and theta 2. Forward kinematics will give me Py, which is another function in terms of theta 1 and theta 2. And this will give me Pz as the function of theta 1 and theta 2. Are you with me so far? So I'm going to work out few more problems wherein the process is going to be the same. I'm not going to do any matrix multiplication by hand. We are going to set up the homogeneous transformations, use MATLAB to solve forward kinematics problem. And then we are going to do a sanity check to see if that forward kinematics problem makes sense. Remember, no matter answer, whatever answer you get, you need to make sure that answer makes sense. Now, let's work out the forward kinematics problem. But before that, let me draw a very nice figure for the two pendulum problem that we are trying to solve. So this is my hinge number 1. This is my frame 0. On this frame 0, this is my x0. This is my y0. There is a non-zero theta. So this is my theta 1. And here, what I have is I have my second frame. And here, what I have is my second link. And here, I'm going to say that I have this coordinate frame. So this is theta 1. This is theta 2. This distance is A2. This distance is A2. And this distance is A4. Are you with me? So I have shown you the coordinate frame, and I'm trying to solve the forward kinematics problem, which means I want to find out the position of the end effector with respect to the zeroth frame. So this is my zeroth frame. This is my first frame. This is my second frame. I'm trying to find out the position of end effector with respect to zeroth frame in the coordinate system of the zeroth frame. Which means what I need to find is I need to find out how far is this end effector from my zeroth frame along x0. Once again, I'm trying to solve this problem. How far is my end effector with respect to the 0th frame along x0? And now you can answer this question very easily. Can you see that? And it's extremely important to note that this angle is theta 1. So this angle, so this is going to become A2 cosine theta 1, and this distance is going to be A4 cosine of theta 1 plus theta 2. You agree with me? Now, why is this? Because notice, this angle is theta 1. These two lines are parallel. This line is extended, so this intercept is theta 1. We are measuring the robot angle from with respect to the frame 1. So this angle is theta 2. So the total angle is theta 1 plus theta 2. Now here, same logic. This distance is going to be A2 sine theta 1, and this distance is going to be A4 sine theta 1 plus theta 2. Are you with me? Now, the only thing I want to check is when I do the forward kinematics problem inside MATLAB, do I get the meaningful equations as shown over here? So without doing any calculation, I can write down my Px, which is the position of the end effector in x, is A2 cosine theta 1 plus A4 cosine theta 1 plus theta 2. Py is A2 sine theta 1 plus A4 sine theta 1 plus theta 2. And can someone tell me Pz? Pz is nothing but summation of these two vertical distances, A1 and A3. Here, A1, A4, A1, A4, A1, and A3 are known. These are the physical lengths of the robot, which means when I try to solve the forward kinematics problem, I substitute the values of theta 1 and theta 2, and then I get the values of Px, Py, and Pz. Everyone understood this? Yes. This is the forward kinematics problem. In the inverse kinematics problem, what I'm going to do is I'm going to substitute the numerical values for Px, Py, and Pz, and I will try to get the values of theta 1 and theta 2. One observation. How many equations do I have? 3. How many unknowns do I have in inverse kinematics? 2. Which means in theory, I just need 2 equations. Clearly, theta 1 and theta 2 does not appear in the Pz equation, so this equation is redundant. So I need to just use these 2 equations and 2 unknowns. It's not an easy problem to solve because I have sines and cosines. So you cannot just add and subtract. You have to square the terms, add those, or convert those into a tangent functions and then solve. But I'm not going to do that mathematical jugglery. We are going to ask MATLAB to solve it. And MATLAB will use these beautiful mathematical numerical algorithms and give me the solutions. Everyone understood about the forward kinematics and inverse kinematics? Now I'm going to go to MATLAB. But before I go on to MATLAB, any questions in the problem setup? Always set up the coordinate system. First, draw the kinematic diagram. Set up the coordinate system using the rules that I have shown. For every joint, find the rotation matrix. Rotation matrix is the product of this standard rotation matrix. This matrix is never gonna change. And this projection matrix. This projection matrix may change depending upon how you are aligning the coordinate systems. Then find out 0H1, which is the homogeneous transformation. Homogeneous transformation captures the positional information and the rotational information. Then what we do is we multiply the homogeneous transformation. Imagine if I have 3 joints, then my final homogeneous transformation will be 0H3, which is 0H1, 1H2, 2H3. Everyone understood this? So you can have a 100-degree of freedom robot and you can just use the homogeneous transformation to solve that robot. After we solve forward kinematics, we get the forward solution. Given the joint angles, find the end effector position. The inverse problem is, given the end effector position, find the joint angles. So what I'm going to do is, now I'm going to go on to the MATLAB and I have already uploaded the solution script for 3 types of robots that we are going to work out. So in today's class, let's discuss the first script. So go on to MATLAB. And I want you to open the forward and inverse kinematics problem for this joint, for this robot. And I'm sure by now you must be expert in MATLAB because you have done that MATLAB on ramp and and already we gave you extensions for 2 days, so I'm sure by now you must be. So I will go line by line what this code is doing, and I would strongly recommend that you go with me line by line and add comments because I have not commented the code. For every forward and inverse kinematics problem, you would use this code as the template. Everyone understood this? The only thing you are going to change is H01, H12, H23, H34, and whatever, how many Hs you have. Everyone understood this? Open your MATLAB and let's start with line by line. First, R parallel to R. This is actually, I'm showing the robot configuration. So what we have is, we have the first revolute joint parallel to the second revolute joint. And then finally, we have the last frame. That's why I said R. So you have 2 revolute joints. First revolute joint is parallel to the second revolute joint. Now, I'm trying to solve this problem symbolically, which means I want to find out a closed form expression in terms of sines and cosines. So I'm defining the symbolic variables. Symbolic variables means they can remain as alphabets. They can remain as symbols. You can swap symbols and numbers and so on and so forth. So first angle is theta1, second angle is theta2, A1, A2, A3, and A4 are the linked lengths. So these are the robot lengths. Everyone understood this? MATLAB does not allow you to define variables starting with a number. So 0H1 is defined or written as H01. H01 is our first homogeneous transformation. Now I want you to look at the notes and make sure that this indeed is the homogeneous transformation. How do we verify? Remember the great matrix. cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, cosine of the first link, A2 cosine theta 1, cosine of the first link, A2 sine theta 1, and then A1. Is this homogeneous transformation correct? Okay. Now go to the second homogeneous transformation. The first 3 by 3 matrix is the same rotation matrix. Cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 1. And now look at the right hand side. The first row, fourth column is A4 cosine theta 2. Remember? Second row, fourth column is A4 sine theta 2. Agreed? Third row, fourth column is not just the vertical distance. So everyone understood that the homogeneous transformations that I have are the same homogeneous transformations that we derived. Now I want to solve forward kinematics, which means multiply these homogeneous transformations. So in the next step, I'm going to multiply these homogeneous transformations. And when I multiply the homogeneous transformation, let me show you what happens. So I'm going to first just run this part. I'm going to just run this part. And I'm going to say evaluate. So when I multiply the homogeneous transformations, what I have, it's extremely important. And I want you to kind of try to see the physics or the physical interpretation of this equation. So this first 3 by 3 rotation matrix, the first 3 by 3 rotation matrix gives me the rotation of end effector with respect to the base frame. Now, there is a meaning for this. I want you to look at this rotation matrix. And let's decipher this. I have this rotation matrix, which is the first 3 by 3 column, first 3 by 3 matrix. Do you agree with me? This rotation matrix gives me the rotation of the end effector with respect to the zeroth frame. Now, can you see that this rotation matrix has the same form: cosine minus sine, sine, and cosine. So can I say that this rotation matrix is nothing but rotation about z naught? Remember, this one means the rotation is about z. Rotation about z naught. And how much of rotation is there? Theta 1 plus theta 2. Now, what that means is the overall rotation of the end effector with respect to the zeroth frame is summation of the first rotation and second rotation. Example, this is my first joint, this is my second joint. First joint went by theta 1, second joint went by theta 2. What is the final rotation with respect to the base axis? Theta 1 plus theta 2 about z naught. That's what this rotation matrix tells me. Everyone understood this? The last part here is telling me the distances between the end effector, which is frame 2, and frame 0 about x0, y0, and z0. Check this out. A4 cosine theta 1 plus theta 2. A2 cosine theta 1. A4 sine theta 1 plus theta 2 plus A2 sine theta 1. And the last one is A1 plus A3. So which means the forward kinematics gives me, as soon as I capture the homogeneous transformation gives me the rotational information, how far the end effector is rotated. Once again, this is the two-dimension, it's a pendulum matrix, a pendulum, theta 1, theta 2. So overall rotation is theta 1 plus theta 2. Are you with me? And the distance between the 0th frame and the second frame is A2 cosine theta 1 plus A4 cosine theta 1 plus theta 2. A4 sine theta 1 plus theta 2 plus A2 sine theta 1. Everyone understood? And the last is A3, A1 plus A3. Everyone understood this? I will give you a minute to process. So we finished one chapter from robotics textbook, by the way. Now let's finish the second chapter. Okay. Now the idea is, here is the next problem. In the forward kinematics, I want to find out what is the orientation of the end effector, what is the position of the end effector. In the inverse kinematics, I want to find out, given the position of the end effector, Px, Py, and Pz, what is theta 1 and theta 2? Once again, when I was a student, it was a torture to solve this equation. Because understand, these are not like apples and oranges type of equation. 2 apples plus 3 oranges is equal to $5. 1 apple is equal to plus 6 oranges is equal to $10. You cannot add and subtract. The reason for that is you are gonna get the sines and cosine terms. So you will have to square and add or convert those sines and cosines into tan. Use the half angle formulae. Find out the inverses, and then it was a whole big mess. But thanks to MATLAB, we can solve it in no time. We don't have to understand how it is internally worked out. At the end of the day, we have to get the solution, if there is a solution, and find the most meaningful or feasible solution. So here is what I'm doing in the next part. I'm capturing Px. Px is the first row, fourth column. Do you agree with me? Py is the second row, fourth column. Pz is the third row, fourth column. So what I have done is I have captured Px, Py, and Pz separately. So this is nothing but those last column, I captured them separately. Everyone understood this? Now I'm gonna solve the inverse kinematics problem, which means I'm going to specify certain numerical value for Px, certain numerical value of Py, certain numerical value of Pz, and ask MATLAB to give me theta 1 and theta 2. A1, A2, A3, and A4, those are constant. Those depend upon robot. So those are fixed. The only variables here are theta 1 and theta 2. To solve this problem, what I'm going to explain to you in the next part. This is not the only way to solve the problem. But what I want to do is, I want to solve a forward kinematics problem, get the solution of that forward kinematics problem, and solve the inverse kinematics problem. That's why the code that I'm gonna show it to you is slightly twisted. And the only reason for this is I'm solving the forward kinematics problem. I'm capturing the solution of the forward kinematics problem, feeding it back into the inverse kinematics problem, and seeing if I'm getting the same angles that I substituted. So I'm going to substitute two angles. Maybe a theta 1 is equal to 0, theta 2 is equal to 35 degrees or anything. Plug those values in these expressions, get Px, Py, Pz. Then I will take those Px, Py, Pz, send it to the solution and try to find out theta 1 and theta 2. Once again, forward kinematics problem will have a unique solution. The inverse kinematics problem may have one solution, may have multiple solutions, or may not have any solution. So when I solve the inverse kinematics problem, I expect lot of solutions to come up. So here is what I'm going to do. Let's go to the next line of the code. So I'm going to solve the forward kinematics problem for certain values. So I'm going to say my A1 is 100, the length A1 is 100, length A2 is 100, length A3 is 135, length A4 is 165. My theta 1 is 0. MATLAB requires angle in radians. So I converted those angles into radians. And my theta 2 is equal to 35. Please understand A1 to A4 are constant. Those are robot lengths. They don't change. T1 and T2 are the angles that they change. So here what I'm doing, please note, this is a symbolic expression, which means Px is expressed in terms of symbols. I am substituting the symbols by the numerical values. So subs is the dpa is variable precision arithmetic. So basically it makes the equation look pretty, but subs will take this symbolic expression px, py, pz, take these symbols. Remember theta 1, theta 2, a1, a2, a3 are sims variable that we defined. Those are symbolic variables, and replace them with these values. These are numbers here. Same thing here. Py, take the symbolic expression, take those symbols, replace them with the numbers. For all forward and inverse kinematics, you are going to use the exact same template. Your H01, H02, or those homogeneous transformations may change. But the jugglery that I'm doing here, you will do the exact same jugglery so that you can check if your forward kinematics and inverse kinematics solutions are correct or incorrect. So right now I'm substituting some values, and I'm going to find out for the forward kinematic solution. So I'm going to find out the forward kinematic solution. And can you see that I get this forward kinematic solution? My Px is 235, my Py is 94, and my Pz is 235. Please run the code and make sure you get the same answers. Everyone understood this? Okay. Now comes the next part, and next part is a little bit tricky that I want to explain to you. So this is actually, I wrote it in a little bit convoluted way. This is not the only way to solve. Here, I'll tell you what I have done. Now, I'm going to use the MATLAB built-in function solve. It's a numerical solver. It has built-in 10 or 15 numerical algorithms that will find out the solution of the algebraic equation. And that algebraic equation could involve transcendental functions like cosine, sine, or some complex functions. So the idea is, I'm asking MATLAB to solve the equation. What equation I'm saying? This equation is only saying Px is equal to Px new, which is the value that we calculated. And I'm substituting A1, A2, A3, A4 as their numerical values. Understand? In this expression, I want to find out T1 and T2, given the value of Px, Py, and that is what this expression is doing. It's a little bit more complex than it needs to be. The other approach is, if you go down, I have worked out another problem. And in that problem, I have been a little bit more simplified. I said Px, which is the expression, is equal to a number. Expression is equal to the second number. Expression is equal to third number. Give me the variables. But here, I made it slightly more complex. So I'm substituting Px is equal to Px new, Py is equal to Py new, and finally, I'm trying to find out the values of theta 1 and theta 2. I would let you play with this code a little bit. It is not difficult. I had to do this jugglery because I wanted to solve the forward kinematics problem and inverse kinematics problem in one shot. If you manually type the forward kinematics problem separately, inverse kinematics problem separately, you don't have to do this. You just have to use the function solve. So then just run this code. And now all of a sudden, you will see that you are gonna get two values of T1. Theta 1 is 43, theta 1 is 0, theta 2 is minus 35, and theta 2 is 35. Which means the end effector position that we got from forward kinematics can be achieved by two sets of angles. If my theta 1 is 43, my theta 2 is minus 35, I get the same end effector position. If my theta 1 is 0, this is numerically 0, and my theta 2 is 35, I get the same position. So in this case, my inverse kinematics problem had two solutions, and MATLAB gave me these two solutions. If you recollect, in the forward kinematics, the value of T1 that we substituted was 0, and value of T2 or theta 2 we substituted was 35. And that's it for today. We'll stop here.